What am I going to do? You don't care about me.
All right, we will get started right away today. We're going to continue chapter 17, notes of course. So titrations is our next section. First, titrations with strong acids, strong bases, and then we'll have another section on titrations with weak acids and bases. We will, at the end of class, go over the iClicker review that we did at the end of class on Wednesday, and then we'll have another review question as well. So let's continue chapter 17 for now. Now I know you all have, if you're in lab at least, you have worked on titrations in lab. And so a titration in general, you have some solution that you're adding a known amount. Let's say your solution is acidic, you're adding a known amount of base to the solution, or if your solution is basic, you're adding a known amount of acid. And adding the base or adding the acid changes the pH of that solution that you have. And so the titration curve shows the change in pH as acid or base is added to that solution. So if we're starting with a strong acid, that means that the solution that you have has a strong acid in it. And we're going to assume when we do these calculations or write out these formulas that we have all of the information. I know when you're doing a titration in lab, you might not know the initial acidity or concentration of ions in solution, and that's part of what titration is used for. But we're going to assume we have all that information and write out the equations of how to determine the pH at different points. And then in certain problems, you might have to do some solving to get the information that you need if you're not provided the information. So here we're assuming we have a strong acid solution and we are titrating with a strong base. The initial pH of the solution, if you have a strong acid in solution, remember that low pH indicates a more acidic solution. So initially, before any base is added, where the volume of the base added is 0, the pH of the solution should be quite low. So here it's about 1. But to actually calculate the pH of the solution, well, if you're adding a strong acid to solution, then all of the acid will dissociate into ions. So as long as you know how much acid is added, you know how much H3O plus is present. So the pH here, you should be able to calculate directly from concentration of the acid added. So we'll say pH is negative log of H3O plus concentration, which would be negative log of the acid concentration since definition of a strong acid is that all of the acid dissociates. That means any acid that's added is going to produce the same amount of H3O plus. Now we see that pH changes along the curve. We'll have different equations or different conditions to calculate pH along that curve. So first, just the initial pH without any base, we can calculate pH with this equation up here. Now between A and C, this is where we have both acid and base present in solution. So some base is added. Remember, adding base means the solution will be less acidic, means that the pH will increase. So it's starting to increase here. At that time, we can still calculate the pH as the negative log of H3O plus. But we can't assume now that initial concentration of HA is the same as H3O plus concentration, because when base is added, it neutralizes some of that H3O plus. So not all of the HA is now H3O plus, some of it is neutralized as H2O. So you'd have to find H3O plus to calculate pH there. Then we've got C, so at the equivalence point. The equivalence point will mean that all of the acid present has reacted with base that has been added. For a strong acid and strong base, they react in a 1-to-1. So you would have moles, N for moles of the strong acid equals moles of the strong base that is added. So the solution is strong acid, strong base is added. They're equal to each other. That means this is a neutral solution now. So the pH will be exactly 7 if you have a strong acid that's being titrated with a strong base. If either one is weak, then the equivalence point is not at a pH of 7. So then past the equivalence point, now we're at D. All of the acid has been neutralized. So there is no H3O plus, or there's approximately 0 H3O plus in solution. So I actually can't calculate pH using this equation because this would be about 0. All of the acid has been neutralized, and now we're increasing pH, meaning more base is being added. So you'd have to calculate pOH. And then use pH equals 14 minus pOH. Oops. Okay, so different parts of the titration curve require different calculations because we have different conditions in the solution now. Now, if we look at the titration curve of a strong base, it looks like you just do a mirror reflection of the strong acid titration curve. So it's very similar, but we're starting with a high pH, which means we have a high OH minus concentration, which means at that time we'd have to calculate pOH. To find pH, we're essentially going backwards now. Then at C, that's the equivalence point. At D, you could calculate pH through H3O plus concentration. So the equivalence point is still 7. Now in this graph, we're saying the solution that you have has a strong base in it, and you're titrating it with a strong acid, adding strong acid to it. Adding strong acid means that the pH then over time will decrease. And that's all I have for strong acid, strong base titrations. We're going to spend most of our time on the weak acid, weak base titrations. But before I move on, do you have questions on this so far? Okay, let's complicate things now. So next section, 17.4, titrations of weak acids and bases. So here's a curve, a titration curve for a weak acid. And we're comparing over here, we're going to compare to strong acid titration curves. Now remember that if you have a strong acid, it fully ionizes. Everything would become, any mole of HA would become H3O plus. H plus would be donated. For a weak acid, most of it remains HA, most of it remains associated, and some becomes H3O plus. So typically, the initial pH of the solution would be higher than if you have a strong acid solution with the same concentration. So our pH here is a little bit higher. And then at C, so at the equivalence point, we said that for strong acid, strong base titrations, the equivalence point pH is 7. But notice here, the equivalence point pH is above 8. This is because in solution, we have a weak acid and a strong base. So at the equivalence point, the base you can think of as is influencing that equivalence point more than the acid. So bases increase pH. If we have a strong base, the equivalence point will be higher than 7 if that's combined with a weak acid. So equivalence point is higher than 7 if you have a weak acid that's titrated with a strong base. And then another difference is that we have a less abrupt pH change near the equivalence point. Or in parentheses, we have this slope here in the B region is a higher slope, so that when the equivalence point is reached, that's a less vertical line, I suppose. So this slope there is a little bit higher. We will go through at each point A, B, C, and D how to calculate pH for a weak acid titrated with a strong base. But first, I have a conceptual question for you. So we're going to assume that we have the same amount of these two acids, acetic acid and benzoic acid. Both are 0.1 molar, so same concentration. Both are not strong acids. They're under the umbrella of weak acids, but one is stronger than the other. So the question is, they're both titrated with 0.1 molar NaOH. Which of these two acids would have a higher pH at the equivalence point? And then the other one would have the lower pH. So think to yourself for a moment and then discuss with someone around you. pKa's are provided for a reason, so consider why the pKa's are there, what information that gives you. Sorry. All right, which of these two acids is the stronger acid? pKa of 4.2. Yes, we have a lower pKa. Lower pKa means stronger acid. That's benzoic acid. So stronger acid here. Stronger acid of the two on the slide. So what does that mean? Will it have a influence on lowering the pH compared to the other or higher? Or we don't know. It will be lower. Let's go back to when we have a strong acid. So strongest acid that we can have with a strong base titration, the pH is 7. And then if we have a weaker base, the pH at the equivalence point will be higher than 7. So now if we're comparing two weaker acids, the stronger one, pH at equivalence point, will be closer to 7, so lower. And the weaker of the two will have a higher pH at equivalence point. So stronger acid will have a lower pH at equivalence point. Yes, go ahead.
So each of them because the global X is going to be low, but because as it's going to be like just slightly lower than one.
Yeah, exactly. So both of the equivalence points of these two are going to be greater than 7. But this benzoic acid will be slightly lower pH at equivalence point because it's a stronger acid than this one, comparing the two. Okay, so now let's go through, so that was just thinking, conceptually not doing a calculation there. Let's go through each part of a weak acid titration curve, titrating it with a strong base, and then how to find pH at each of those points. And again, we're assuming that we have information needed. So this one, we have to assume that we know initial concentration of the acid added. So for part A, at point A, this is where there's no base added to solution yet. So we just have a solution with a weak acid and we're asked to find the pH. Remember, we did ice tables for this, but we can assume certain things to make it simpler. If you have HA only in solution, no base yet, it reacts with water and it will form A- and H3O+ because it's an acid. Not all of the HA dissociates into A- and H3O+. So HA will decrease by some amount, A- increases by some amount, H3O+ increases by some amount. We'll label that as X. I'm just simplifying an ice table essentially on this slide. So at equilibrium, the K, which in this case, since an acid is added to solution, Ka, would be A- concentration, H3O+ concentration. HA concentration, and at equilibrium, that is approximately X times X, so X squared, over initial concentration of HA. This is where we are assuming that HA is much larger than the value of X. So we can approximate HA concentration minus X as just being the HA concentration. Then setting this equal to Ka, we could solve for X. We're going to be deriving an equation at the bottom. That's the key equation that you'll use at this point. Remember, we're trying to calculate pH, so we need H3O+ concentration. At equilibrium, that's equal to X. So we can rearrange this equation here, assuming we know Ka as well. So we will have x squared equals Ka times the concentration of Ha. And so x equals the square root of that. At equilibrium, concentration of H3O plus is equal to X. So with pH being negative log of H3O plus, that is negative log of the square root of Ka times the initial concentration of Ha. So the work that we did up here was to explain, to derive this final equation. So now if you're asked for the pH of a solution with a weak acid, no base has been added yet, you can just use this equation. You know, initial concentration of Ha, and you have the Ka, then you take the negative log of the square root of the product of those two, and that will give you pH. So you don't have to go through all these steps to find pH at that point. So we use that equation to find the initial pH. And this only works for part A, or for point A, where we have not added any base yet. That's because once base is added, it's going to react with H3O plus, and we won't have as much H3O plus present in solution. That's why the pH is increasing. So we can use this for A, but once we get to B, where some base is added, we have a different a different equation that we'll use. Are we ready for B? I'm going to assume silence means yes, but feel free to stop me if you need to. So B. We are now between the initial pH and the equivalence point. We have both acid and base present in solution. This is where a buffer solution exists. Notice that the pH isn't changing very drastically here, and the point of a buffer solution is to resist change in pH. We make a buffer solution by adding acid and base. So here we have a buffer solution. So we can use the equation that we had for buffer solutions to find the pH, which was the Henderson-Hasselbalch. So at B, in that range between initial pH and equivalence point, we can use pH equals pKa, so of the acid Ha, negative log of the Ka, plus log of a minus concentration divided by Ha concentration. We use that equation, but at this point, how would we know what A minus is? Thinking in terms of the ice table, Ha reacting with OH minus, they react together, so we're going to decrease in concentration of those two and increase in concentration of A minus. Adding a strong base to solution, all of that base is going to react with the weak acid that's there. And remember, when you're doing a titration and you have the strong base, in this case in the burette, you can see exactly how much base is being added to solution. That will tell you the value of X. All of the OH is going to be reacted, so the concentration of A will be the concentration of base that's added. So all of the strong base Okay, so X is amount of OH minus added. We're assuming that you'd be able to know what that amount is because you can read the burette. And then X, because all of the strong base reacts with HA, the amount of A minus present increases by X. So we have that there. Okay, so any of those more plateau areas of the titration curve, you can use Henderson-Hasselbalch equation because a buffer solution exists there. At the equivalence point, this is when, you ready for C? Okay, so this is when all of the acid has now reacted with the base, so there's no more HA present in solution. So notice our reaction equation has changed again. No HA on a reactant side, it's all A minus, and then that reacting with H2O would produce HA and OH minus. So now this reaction equation, what's reacting with the water is a base. So we're going to need a K expression, a K value, but we can't use Ka anymore because left-hand side doesn't have an acid, it has the base. So we need to find Kb, which is Kw, constant value provided on your sheet, divided by Ka. So that would be your first step, is to find Kb. This is, we'll write it again. Kb is approximate, well, let's write out the equation. I'm getting ahead of myself. HA times OH minus concentration divided by A minus. And this is approximately, we're increasing in product, decreasing reactant, X squared over A minus concentration. So rearranging in the same way as we did for that first part, X squared, or X on its own, is equal to the concentration of OH minus. So we'll solve for X, which will be square root of Kb times A minus. And we can calculate POH in this case. So concentration of OH minus here is equal to X, which is equal to the square root of Kb times the A minus concentration. There's no H3O plus here, so we can't calculate pH directly. First, POH is calculated, and then we can find pH from that. Okay, we've got one more point, and that's D. This is after the equivalence point. So at this point, all of the H3O plus, all of the acid, the HA has reacted with the base. So now all that we're doing is adding more base, increasing the pH. So past that point, the pOH or the pH depends almost completely on the excess OH minus that's added. So you're adding more base to that solution that already reached the equivalence point. So the pH depends on that excess amount. We can't, again, calculate pH directly, so we have pOH. Okay, so extra OH minus added will indicate what that pOH is going to be. Then we've got pH. So when you're ready, go to this next slide. You have a learning check about a titration. So we have, I'll leave this up in case you're still writing, but on that slide, there's 40 milliliters of a 0.5 molar formic acid solution. We have the Ka of formic acid. Formic acid is not a strong acid, not on our strong acid list, so it's a weak acid. It's titrated with 0.5 molar sodium hydroxide. So we have a weak acid titrated with a strong base. The next sentence says, assume that less than 5% of the acid ionizes in solution. So that means of all of the acid that's added, less than 5% of it becomes the conjugate base in H3O+. All that tells us really is that it's a weak acid, that we can assume initial concentration of the acid is equal to equilibrium concentration. So then you're asked to determine the pH at 3 different points. First is at the beginning, so no base is added. What is the pH of a 0.5 molar formic acid solution? Then at the equivalence point, so assuming enough base is added to neutralize all of the acid. And then third is past the equivalence point, an extra 2 milliliters of sodium hydroxide is added. So then what's the pH at that point? So I'll give you all a few minutes to get started, and then we'll go through them together. Actually, here's what we'll do. I'm still going to give you time to work on it. Of course, start with number 1, and then if you have time, go to the next 2. In a few minutes, we'll review number 1, and then on Monday, we'll review 2 and 3. I just want to have time to show 2 more slides, the weak base titration slide and the polyprotic acid titration slide, and then we'll go back to doing that Gen Chem 1 review. So we're going to stop Chapter 17 notes for today after that first part of the question, and then we'll pick up on Monday. So 2 minutes and we'll review. Okay, let's go through this. So prior to adding any NaOH, that is where we talked about point A, the initial pH of the solution. We can just use this equation here. Negative log square root Ka times initial concentration. In this case, the HA is HCHO2. All right, so negative log of Ka 1.8 times 10 to the negative 4 times initial concentration 0.500 molar. So pH initially is 2.02. And then as this solution is titrated with base, the pH will start to increase. So for 2 and 3, we'll have different equations to find the pH. And the pH should be higher than 2.02. Okay, so we'll finish this problem in class on Monday. It is in the book, so if you need help going through this for the Achieve, for example, this whole example is in the book, and they explain each step, so you can use that as well. Same chapter and section as how our notes are organized. Questions before we move to Gen Chem 1 review? Okay. Okay, so let's talk about this one that you did at the end of class. We have a selenium ion with a 2- charge, mass number of 76, and we need to determine neutrons, protons, and electrons in this. Oh, that shouldn't have said neutral. In this isotope, it is not neutral. Okay, so mass number 76, what does that tell us? Number of protons and neutrons. So protons and neutrons in an atom, they have mass. Electrons, we assume, have 0 mass. So the total mass, 76, is protons. I'm going to abbreviate that as P plus and N for neutrons. So what do we do next? What other information can we gather about selenium? Periodic table number, what does that tell us? Number of protons, yes. So the number of protons for an element never changes. That is the identity of an element, is the number of protons in its nucleus. So selenium always has 34, is that right? Okay, always has 34 protons, so 76 equals 34 plus neutron. So number of protons is 34. Neutrons is 76 minus 34 is 42. So difference between mass and number of protons. Now we need number of electrons. Selenium has in this ion a 2- charge. Remember, protons positive, electrons negative. Minus charge means you have more electrons than you have protons. 2- means there's 2 more electrons than you have protons. And then you also, it's important to remember that protons cannot change. So we can't say there's 34 electrons and 32 protons, because that's a different element. That's not selenium anymore. So you always have the same number of protons as what's on the periodic table. We have a 2- charge. So that means electrons needs to be 2 greater than 34. So 36 electrons. Okay, I've got 2 more review questions for you. The first one is just one question. So I'll put this on the board in a minute. You have 2 isotopes of chlorine with different percent. abundance. Find, using those two isotopes and the relative percent abundance, what is the average atomic mass of chlorine. And then once this is done, I have one more. So we need to spend no more than 4 more minutes on this.
Oh, yeah.
So about 15 seconds. It's like just about everyone's in. Okay, gonna end it here. Okay, will someone please describe how you solved this? Yes.
Convert the abundance to decimal, then multiply the abundance by corresponding isotopic mass and do something.
Okay, so you convert the abundance to a decimal. You have to involve the relative abundance here. If you just add the two masses, divide by 2, that doesn't give you the actual average atomic mass of Earth because the relative abundance is important here. If one of the isotopes is more abundant than the other, that has a larger influence on the average mass, I will say. So yes, we take the relative abundance, convert it to a decimal, multiply that. So we'd have 0.7577 times its corresponding its isotope mass, and then add all that together. So that will be 0.7577 times 34.97 plus 0.24323 times 36.97, and then this will get you to 35.45. Atomic mass unit. So that will be the average atomic mass. Okay, next question, next review question is atomic size. So thinking about a periodic trend, we're jumping all over for this review. Periodic trends, you'll have 2 questions, each has 2 elements on them, and you're just selecting the larger one. We're going to review this, so don't pack up yet. Mm-hmm. No. There's also a trend going down the column.
So down is larger.
Okay, everyone submit? Okay. So periodic trend for size. Going down a column that's perhaps easier to remember. Remember, each of these numbers represent an energy level of electrons. So if you have electrons at the 7th energy level, that's furthest away from the nucleus. First energy level is really close. So as you go down column, size increases. As you go left to right across a period, electrons are in the same energy level, but you're increasing the number of protons in the nucleus. So the nucleus pulls those electrons in that energy level closer, and atomic size decreases across a period. So fluorine is smaller than oxygen, which is smaller than nitrogen. So if we're pointing arrows towards the largest atoms, that will be bottom left. So first you compared silicon and sulfur, or at least I think that was one of them, right? Yeah, maybe? Okay, thank you. Silicon and sulfur, so they're in the same period. So we think about this trend here, larger atoms are to the left if they're in the same period. So silicon is larger than sulfur. And then we had sulfur and selenium, which are in the same column, but selenium is one row lower. So selenium is larger than sulfur. Yes. Si and Cl? Oh, okay. So then that would still be true. Silicon is larger than chlorine because it's further to the left. Thank you. All right. Thanks, everybody. See you on Monday. Oh, I forgot to talk about polyprotic acids. Use your book if you need it. Email me if you need help. Thanks, you too. Sorry. I just want to stop the